Have you ever wondered what the universe looked like before the stars we see today were even born? Imagine being able to peer so deeply into space that every faint point of light becomes a clue to a story billions of years in the making. Right now, as you watch this video, NASA is preparing one of the most ambitious space observatories ever built. It isn't designed simply to capture beautiful images. Its mission is far more extraordinary. The Nancy Grace Roman Space Telescope could completely transform our understanding of dark energy, reveal thousands of hidden worlds beyond our solar system, and uncover some of the oldest galaxies ever formed. But before this incredible observatory begins its journey through space, scientists and engineers are racing against time to prepare it for one of the most challenging launches in NASA's history. For decades, every revolutionary telescope has changed humanity's place in the cosmos. The Hubble Space Telescope revealed that the universe was far more beautiful than anyone imagined. The James Webb Space Telescope looked farther into the past than ever before, showing us galaxies that existed only a few 100 million years after the Big Bang. Yet despite these astonishing discoveries, enormous mysteries remain unsolved. What exactly is causing the universe to expand faster and faster? Where are the countless invisible planets hiding throughout our galaxy? Why does most of the cosmos seem to consist of something we cannot even see? These questions have puzzled astronomers for generations. Now NASA believes it finally has an instrument capable of bringing us closer than ever to the answers. Unlike previous observatories, the Roman Space Telescope was never intended to focus on just one tiny corner of the sky. Instead, it will observe enormous regions of the universe all at once. Imagine replacing a flashlight with a powerful floodlight. Instead of illuminating a single object, you suddenly reveal an entire landscape filled with countless hidden details. That is exactly what Roman is expected to do for astronomy. This remarkable observatory carries a primary mirror measuring to 0.4 meters across, matching the size of Hubble's famous mirror. But appearances can be deceiving. While Hubble captures incredibly detailed images of relatively small areas, Roman's revolutionary wide-field instrument will allow astronomers to see an area nearly 100 times larger in a single observation while maintaining exceptional resolution. To appreciate how extraordinary this is, imagine taking a photograph of a city skyline. Hubble would show you one magnificent skyscraper in incredible detail. Roman, however, could capture the entire city with nearly the same sharpness, revealing millions of buildings simultaneously. That enormous leap in capability is exactly why astronomers around the world are so excited. Building such an instrument has required years of engineering unlike anything attempted before. Every mirror, every sensor, every electronic component must survive the violent forces of launch before operating flawlessly. In the unforgiving vacuum of space, inside NASA's clean rooms, engineers dressed in full protective suits carefully inspect every component. Dust particles invisible to the naked eye could interfere with observations so sensitive that Roman will detect light which has traveled for billions of years before finally reaching its mirrors. Nothing can be left to chance. Every cable is tested repeatedly. Every detector is calibrated with astonishing precision. Every bolt is inspected countless times. Preparing a telescope of this complexity is less like assembling a machine and more like conducting an orchestra where thousands of individual parts must perform together in perfect harmony. The observatory itself represents decades of scientific ambition. Originally known as the Wide Field Infrared Survey Telescope, or WIRST, the mission evolved dramatically as new technologies emerged and astronomical priorities shifted. Eventually, NASA renamed the observatory in honor of Nancy Grace Roman, often called the Mother of Hubble. Long before space telescopes became household names, Nancy Grace Roman was fighting to convince the scientific community that astronomy belonged above Earth's atmosphere. During an era when few women held leadership positions in science, she became one of NASA's first chief astronomers. Her determination laid the foundation for generations of discoveries that continue to reshape our understanding of the universe. Naming this groundbreaking observatory after her is more than symbolic. It represents the continuation of a vision she helped create decades ago. But perhaps the most exciting aspect of Roman is not the telescope itself. It is what the telescope is searching for. One of Roman's primary objectives is to investigate one of the greatest mysteries in all of modern physics: dark energy. When astronomers first realized that the universe was expanding, they expected gravity to slow that expansion over time. Instead, observations revealed something astonishing. The expansion wasn't slowing down, it was accelerating. Some invisible force appeared to be pushing galaxies farther apart at increasing speeds. No one had predicted it. No one fully understood it. Scientists eventually gave this mysterious phenomenon a name: dark energy. Today, researchers estimate that dark energy makes up nearly 70% of the entire universe. Think about that for a moment. Everything we can see, every planet, every star, every galaxy, every black hole, every cloud of glowing gas accounts for only a tiny fraction of reality. The overwhelming majority of the cosmos consists of something humanity has never directly detected. It surrounds us. It shapes the evolution of galaxies. It influences the fate of the universe itself. Yet we still have no definitive explanation for what it actually is. Roman was designed specifically to attack this mystery from multiple directions at once. Rather than relying on a single experiment, it will conduct enormous surveys involving hundreds of millions of galaxies, spread across cosmic history. By measuring how these galaxies cluster together, and how space itself stretches over billions of years, scientists hope to build the most accurate map of cosmic expansion ever created. Every observation becomes another piece of an unimaginably large puzzle. Patterns invisible today may suddenly emerge once enough galaxies have been measured. Tiny differences in brightness, slight distortions caused by gravity, almost imperceptible changes in distance. Each one contains valuable information about the invisible forces shaping the universe. Roman's extraordinary sensitivity will also allow astronomers to observe gravitational lensing on an unprecedented scale. According to Einstein's theory of general relativity, massive objects bend space itself. Light traveling through this curved space follows distorted parts, creating subtle changes in the appearance of distant galaxies. These distortions are incredibly small. Most are impossible to notice with ordinary telescopes. But Roman was built precisely for measurements this delicate. By analyzing billions of these tiny distortions, astronomers can construct enormous maps showing where invisible matter is distributed throughout the universe. Since dark matter cannot be observed directly, gravitational lensing offers one of the few reliable methods for tracing its presence. Together, dark matter and dark energy form the hidden framework upon which the visible universe is built. Understanding them could fundamentally change modern physics. Yet Roman's mission extends far beyond cosmology. In another astonishing scientific campaign, the telescope will search for entirely new planetary systems scattered throughout the Milky Way. Thousands of them, perhaps tens of thousands. And unlike many previous planet-hunting missions, Roman will focus on worlds that are almost impossible to detect using conventional techniques. Most of the exoplanets discovered over the past 3 decades have been found because they either pass directly in front of their stars, or because their gravity causes their stars to wobble ever so slightly. These techniques have revolutionized astronomy, revealing that planets are far more common than anyone once believed, but they also have limitations. They are naturally biased toward finding large planets orbiting close to their stars. Entire populations of distant worlds remain hidden, simply because our current methods struggle to detect them. Roman will approach the problem from an entirely different angle. Its secret weapon is a phenomenon predicted by Albert Einstein more than a century ago: gravitational microlensing. Imagine a distant star shining toward Earth from thousands of light years away. Under normal circumstances, that tiny point of light would remain almost unchanged for centuries. But if another star happens to pass almost perfectly between us and that distant background star, something remarkable occurs. The gravity of the foreground star bends space itself. Instead of blocking the light, the star acts like a natural cosmic magnifying glass. For a brief period, the background star appears brighter, sometimes much brighter. If that foreground star happens to possess planets, those planets create tiny additional distortions in the light. The resulting brightness curve changes in very specific ways, allowing astronomers to infer not only the existence of the planets but also estimate their masses and distances from their host stars. These events are incredibly rare. The alignment must be almost perfect. The brightening may last only days or weeks, And once the event ends, it never repeats. Missing one means losing that opportunity forever. This is where Roman's enormous field of view becomes revolutionary. Instead of monitoring a handful of stars, it will continuously observe millions upon millions of stars toward the crowded center of the Milky Way, patiently waiting for these fleeting alignments to occur. Statistically, the more stars you watch, the more microlensing events you will catch. Astronomers expect Roman to detect thousands of new exoplanets, including worlds unlike anything previously observed. Some may resemble Jupiter or budding far from their stars. Others could be icy planets wandering in the outer regions of distant solar systems. Perhaps most intriguingly, Roman may discover large numbers of rogue planets, worlds that drift through interstellar space, completely alone. Imagine an entire planet with no sunrise, no sunset, no parent star illuminating its skies, just endless darkness stretching across the galaxy. For decades, astronomers suspected such lonely worlds might exist. Violent gravitational interactions inside young planetary systems can eject planets into deep space, where they wander for billions of years without belonging to any solar system at all. Detecting these invisible travelers is extraordinarily difficult because they emit almost no light. Yet gravitational microlensing offers a rare opportunity. Even a dark planet can briefly reveal itself if its gravity bends the light of a distant star. Roman may discover hundreds or even thousands of these mysterious cosmic orphans. Each detection would tell a story about how planetary systems form, evolve, and sometimes violently destroy themselves. The telescope's observations could dramatically reshape our understanding of how common planetary systems like our own truly are. Could our solar system actually be unusual? Or is it merely one example among billions following similar patterns throughout the galaxy? Roman may finally provide the statistical evidence astronomers have sought for decades. But perhaps its greatest strength lies not in answering questions. It lies in discovering questions nobody has thought to ask. History has repeatedly demonstrated that every major astronomical observatory ends up making discoveries completely unrelated to its original mission. When Hubble launched, few imagined it would reveal protoplanetary disks surrounding newborn stars. When the Kepler Space Telescope began searching for planets, no one expected it to uncover entirely new categories of planetary systems. Even the James Webb Space Telescope surprised astronomers almost immediately by detecting unexpectedly massive galaxies in the early universe objects that challenged some existing models of galaxy formation. The universe has a remarkable habit of refusing to behave exactly as scientists expect. Roman is almost certain to continue that tradition, because it will survey enormous regions of space with unprecedented depth. Researchers anticipate finding strange phenomena that have never been observed before, simply because no telescope has ever looked at the sky in quite this way. There may be unusual stellar explosions, previously unknown types of variable stars, rare gravitational lensing events, ancient galaxy clusters hidden behind curtains of dust, perhaps even entirely new classes of astronomical objects waiting patiently to be noticed. For the very first time, some of the most significant discoveries in science begin with a simple sentence: "We weren't expecting that." Preparing Roman for launch has therefore become one of NASA's highest priorities. Every subsystem must operate flawlessly before a single rocket engine ignites. The observatory undergoes an extraordinary sequence of environmental tests designed to simulate every challenge it will face during its journey into space. Engineers expose the spacecraft to violent vibrations that can imitate the immense shaking produced during launch. The forces are so intense that even microscopic structural weaknesses could become catastrophic failures. Massive hydraulic systems rattle the observatory in every direction, while hundreds of sensors record the slightest movement. If anything shifts unexpectedly, engineers investigate immediately. Next comes acoustic testing. Inside specialized chambers, gigantic speakers generate deafening sound levels comparable to those produced by powerful rocket engines. Although no flames are present, the pressure waves alone are capable of damaging sensitive equipment. The observatory must prove it can withstand this invisible assault before leaving Earth. Then comes one of the most demanding examinations of all: thermal vacuum testing. Inside enormous vacuum chambers, engineers remove nearly all the air, recreating the emptiness of space itself. Powerful cooling systems lower temperatures to levels far below anything experienced on Earth. Other equipment simulates the intense heat of direct sunlight. Over days and weeks, Roman repeatedly cycles between extreme hot and cold conditions while every electronic system continues operating. In space, there is no atmosphere to moderate temperature. One side of a spacecraft may bake in sunlight while another remains hundreds of degrees colder. Components expand, they contract. Materials behave differently than they do on Earth. Only exhaustive testing can reveal hidden problems before launch. Every successful milestone brings Roman one step closer to its destination. But even after launch, its journey will only be beginning. Unlike Hubble, which orbits relatively close to Earth, Roman is headed nearly 1.5 million kilometers away to a region known as the second Sun-Earth Lagrange point, often abbreviated as L2. At first glance, sending a telescope so far from Earth may seem unnecessarily risky. Why not keep it nearby where astronauts could potentially repair it? The answer lies in stability. At L2, the combined gravitational pull of the Earth and the Sun creates an environment where a spacecraft can remain in a relatively stable orbit while keeping the Sun, Earth, and Moon all in roughly the same direction. This geometry offers enormous advantages. A large sunshield can permanently block heat and stray light. Sensitive infrared instruments remain cold. The telescope enjoys an uninterrupted view of deep space, without Earth constantly passing in front of its field of vision. For an observatory designed to detect unimaginably faint signals from across the cosmos, such stability is invaluable.
Reaching L2, however, is far from simple. The journey will take approximately 1 month, carrying the observatory farther from Earth than any crewed spacecraft has ever traveled. During that voyage, Roman will undergo one of the most delicate sequences of mechanical operations in modern space: exploration. Every deployment must occur exactly as planned. Protective covers will separate. Solar arrays will unfold. Communication antennas will lock into position. The massive sunshield will extend, ensuring that sunlight never reaches the telescope's most sensitive instruments. Unlike many systems on Earth, there are no second chances in deep space. If a deployment mechanism fails millions of kilometers away, there is no repair crew waiting just around the corner. Every hinge, every motor, every release mechanism has therefore been tested countless times before launch. Engineers often describe space missions as exercises in controlled uncertainty. They can prepare for nearly every imaginable scenario. But space always has a way of introducing unexpected challenges. Tiny particles of dust race through the solar system at astonishing speeds. Solar radiation constantly bombards electronics. Temperature fluctuations slowly stress materials over many years. Even the gentle pressure of sunlight itself exerts a measurable force on spacecraft. Roman has been designed to survive all of it. Its guidance systems will maintain extraordinary pointing accuracy, allowing the telescope to remain almost perfectly still while collecting faint light from galaxies billions of light years away. To appreciate the precision involved, imagine standing on Earth and trying to keep a laser pointer aimed at a coin placed thousands of kilometers away without allowing the beam to drift by even a fraction of a millimeter. That level of stability is astonishing enough. Now imagine maintaining it continuously for hours while orbiting through space. That is the kind of engineering challenge Roman has been built to overcome. The observatory's detectors themselves represent another remarkable achievement. Each sensor must capture incredibly weak infrared light without introducing electronic noise that could overwhelm the faint signals arriving from distant galaxies. Every photon matters. Some of the light Roman will detect began its journey long before our solar system even existed. When that ancient light finally reaches the telescope, only a tiny number of photons may strike each detector every second. The instruments must distinguish those precious signals from every possible source of interference. It is an extraordinary balancing act between sensitivity, stability, and precision. Yet perhaps the most exciting aspect of Roman's mission is not what scientists already expect to find. It is what nobody can predict. Astronomy has repeatedly demonstrated that whenever humanity builds a more powerful window into the universe, reality proves even stranger than imagination. Centuries ago, Galileo pointed a small telescope toward Jupiter and discovered 4 large moons orbiting another world. That single observation forever changed humanity's understanding of its place in the cosmos. In the 20th century, radio telescopes uncovered pulsars rapidly spinning neutron stars that initially seemed so mysterious some researchers jokingly labeled them little green men. More recently, gravitational wave observatories revealed an entirely new way of observing the universe, detecting ripples in spacetime itself created by merging black holes billions of light-years away. None of these discoveries were anticipated in their final form. Nature consistently surprises us. Roman may become the next great source of scientific astonishment. Its immense surveys could reveal unexpected structures stretching across billions of light-years. It might detect rare cosmic explosions unlike any previously recorded. It could uncover populations of dwarf galaxies so faint they have remained invisible until now. Perhaps it will observe gravitational lenses so powerful they expose galaxies from an air astronomers never thought accessible. Or perhaps the greatest discovery has not yet been imagined by anyone alive today. Science advances most dramatically when observations force theories to evolve. If Roman finds something that does not fit our current understanding of physics, astronomers will not see that as failure. They will see opportunity. Every contradiction between theory and observation is an invitation to learn something fundamentally new. One of Roman's most ambitious long-term goals is to construct an enormous three-dimensional map of the universe, not simply where galaxies appear in the sky, but where they exist across both space and cosmic time. Because light travels at a finite speed, observing distant galaxies is equivalent to looking into the past. A galaxy located 1 billion light-years away appears as it existed 1 billion years ago. Another located 10 billion light-years away reveals conditions when the universe itself was still relatively young. Roman will combine observations spanning enormous distances to reconstruct how cosmic structures have evolved over billions of years. Scientists often compare this process to studying the growth of a forest. A single tree reveals only limited information, but observing millions of trees of different ages allows researchers to reconstruct how an entire ecosystem develops. Roman will perform that kind of analysis on a universal scale by examining hundreds of millions of galaxies across different eras. Astronomers hope to understand how matter gradually assembled into the breathtaking cosmic web we observe today. This immense network of galaxies, clusters, and invisible dark matter filaments stretches across the observable universe. Like an unimaginably vast three-dimensional spider web, galaxies do not appear randomly scattered. Instead, gravity has spent billions of years organizing matter into interconnected structures separated by enormous empty voids. Roman surveys will measure this cosmic architecture with unprecedented precision. Every new measurement helps answer one of astronomy's oldest questions. How did the universe evolve from the nearly uniform conditions after the Big Bang into the richly structured cosmos we inhabit today? The answers are hidden within patterns too large for any previous telescope to fully capture. Roman's combination of wide coverage and exceptional sensitivity makes it uniquely suited for this task. The observatory will also work alongside other groundbreaking facilities rather than replacing them. James Webb excels at studying individual objects in extraordinary detail. Roman will identify countless fascinating targets spread across the sky. Together, they form a remarkably powerful partnership. Roman discovers, Webb investigates. Ground-based observatories confirm. Future telescopes expand. Modern astronomy increasingly resembles a coordinated global network, rather than isolated missions operating independently. Each observatory contributes a different piece of the larger puzzle. Data collected by Roman will likely fuel scientific research for decades. After its primary mission concludes, students currently beginning their education may eventually build entire careers analyzing observations that have not yet been recorded. Future discoveries may emerge from data archived long after the spacecraft itself has completed its work. This has happened before. Astronomers continue making important discoveries, using observations gathered years even decades earlier by previous missions. The true value of a great observatory often grows with time. As computing power advances and analytical techniques improve, researchers uncover hidden information that earlier generations simply could not detect. Roman's enormous databases may therefore become one of the most valuable scientific resources of the 21st century. Some of its greatest discoveries may not happen during the mission itself. They may occur years later, when fresh ideas meet an extraordinary archive of observations gathered from one of humanity's most ambitious eyes on the cosmos.